Hi guys, welcome back to another video on my channel. I know it's been a while, and I keep saying that every video, but this video is being made because someone pointed out a flaw in one of my videos. A video that I was very proud of, in fact, because someone had challenged me to that question and I had solved it, but it seems I had not been careful. Uh, Moving on, I just want to request people who want to, point out, who want to give me constructive feedback in the comment section, is please be specific because I can't tell the difference between trolls and legitimate well-wishers on my channel. And the only thing that bridges that gap, that makes me determine which is which, distinguish between the two, is constructive feedback. So if you just elaborate, the timestamp or the reference in the first comment that you post, and you can edit comments on YouTube. So even if you forget, please add that specific reference, either timestamp or literature, to point out the mistake, and then I can evaluate. I can tell for myself if there actually needs to be an amendment to the video. In this case, I'm making a fresh video. I will be deleting the old one. The old one, meaning the two videos. I will be deleting the first one. I'm keeping the second one because that's an entirely different question in its regard. I will tell people to probably ignore the last result. We'll see how it goes. Anyways, let's get started. The question that we have is actually an integral of an infinite product. So I equals integral from 0 to infinity, the product from n equals 1 to infinity, of secant, hyperbolic secant, sec h, of x over 2 to the n plus 1 divided by secant of x over 2 to the n plus 1 quantity raised to 2 to the n dx. So first of all, let's do the product, because in the product there's no real dependence, on when I'm talking of the product, I mean in the bounds of the product there's no explicit dependence on the x, and therefore we can treat this as an independent problem. So we call that P. Now notice what we can do is, we don't like these these reciprocal functions. We can easily convert the hyperbolic secant and the regular secant into the respective 1 over cosh and 1 over cosine. When we do that, we can achieve a common denominator. We will have hyperbolic cosine cosh of 2 to the minus n of x. I'm writing x over 2 to the n is 2 to the minus n of x plus 1 divided by cosine of 2 to the minus n times x plus 1, quantity to the 2 to the nth power. But we also have that extra term from both the numerator and the denominator, since it was a reciprocal relationship. We have cosine of 2 to the minus n times x divided by cosh of 2 to the minus n times x, quantity to the 2 to the n power. Again, and the product is from n equals 1 to infinity. Moving on, what we can do is we can actually simplify this. So there's two nice properties. There's two nice formulas that we can use, and I think I should write them down. I think I forgot to write them. First of all is 1 plus cosh of 2x is 2 cosh squared of x. So you see the angle has been halved and the quantity, the function has been squared. Similarly, we have another one for the cosine. 1 plus cosine of 2x, 2 cosine squared x. Just the same thing. It's as if we just remove the h from the cosh. It's just the same identity. So using that, we notice that we can use that in the numerator. So we get a factor of 2 from the numerator and the denominator, because we're doing that in both the top floor and the bottom floor. The 2 will cancel, so I'm not writing that out. But we will have cosh of 2 to the minus n minus 1 times x, because the angle has been halved. So we have x over 2 times 2 to the minus n, which is 2 to the minus n minus 1 times x, divided by cosine of 2 to the minus n minus 1 times x. But that's not all. Remember, we are also squaring in both cases. Now that square manifests and accumulates in the power that we already have. The power we already had was 2 to the n. And when we multiply 2 to that, we will get 2 to the 2n plus, or 2 to the n plus 1, sorry. This is just using a rule of exponents. I'm skipping a few steps. Okay, and then the second term is as it is, cosine of 2 to the minus n times x divided by cosh of 2 to the minus n times x, quantity to the 2 to the nth power. Now, we can actually reindex this first product. We can start when we notice n equals 1, we have 2 to the minus 2. So it's as if starting our sum from n equals 2. So when we do that, we can index this as product from n equals 2 to infinity, cosh of 2 to the minus n times x divided by cosine of 2 to the minus n times x, quantity to the 2 to the n, because notice that this was the same thing that's happening even in the power. So like it's practically like changing n plus 1 to n. All that does is just change our lower bound of integration of products. I've been doing so many integrations that lower bounds get and upper bounds get associated with the integral. I'm sorry if I misspeak. Meanwhile, in the second term, there's nothing really going on. We can just keep the same lower bounds of doing the product. So n equals 1 to infinity, product of cosine of 2 to the minus n times x divided by cosh of 2 to the minus n times x, quantity to the 2 to the nth power. Now, notice that they're almost reciprocals of each other. There's a cosh in the numerator here and there's a cosh in the denominator here. There's a cosine in the denominator here and the cosine in the numerator here. These terms would actually cancel if they were under a common product. Now, how do we achieve that common product? Well, notice that this product is just the same as this. I mean, in the sense of the index here. It's just that this starts with 1 and this starts with 2. So if we just remove that n equals 1 term, then we will have the second product start from n equals 2 as well. So what I mean remove is just write that term explicitly down and then combine the other remaining terms in the second product as a product from n equals 2 to infinity. So the first term, n equals 1 term, is cosine of 2 to the minus 1 of x, which is to the 2 to the 1 power. So that's cosine squared of x by 2 divided by cosh squared of x by 2, because that power also applies to the denominator. So then we have the product from n equals 2 to infinity, because we remove that term, and then we can start the second sum from n equals 2 and then combine, I keep saying sum, I'm sorry, a product. We can combine both products under a common product symbol. So product from n equals 2 to infinity of cosh of 2 to the minus n times x cosine of 2 to the minus n times x divided by cosine of 2 to the minus n times x times cosh of 2 to the minus n times x, quantity raised to the 2 to the n. Now, notice everything cancels in this grand product. Everything that's being raised to power 2 to the n, it becomes 1. It factors off this cosh with that cosh, this cosine with that cosine, and then we have 1 to the power 2 to the n multiplied by itself, because each term for all n inside that's the base of 2 to the n is going to be 1. 1 raised to any power is 1. 1 multiplied with itself infinite times is also 1. Thankfully, that's how the algebra works. That's how our number system is. So the entire thing just collapses because this telescopes in a way to give us cosine squared of x by 2 divided by cosh squared of x by 2. And that's it. That's P. That's this scary looking product. It's P. It's done. We solved it. But that's just half the problem. The remaining half is integrating from 0 to infinity of cosine squared x by 2 divided by cosh squared x by 2 dx. Let's first change x by 2 to x using a trivial kind of substitution. So we get 2 as the factor up front, integral from 0 to infinity cosine squared of x divided by cosh squared of x dx. Now we want to use integration by parts. So we can write cosh squared, that's in the denominator and the numerator, as secant, hyperbolic secant squared, sec h squared. Now sec h squared has antiderivative tan h of x, the tanh, the hyperbolic tangent function. But we're not going to consider just that. We're going to consider tanh of x minus 1 as its antiderivative in the integration by parts. You will see why. It's not clear from this step onwards. You will see when we're trying to actually evaluate that it'll actually be very, very useful. So once we do that, so we're going to take the antiderivative of secant h squared. That becomes 2, which was from the prefactor that we had. Tanh x minus 1 times cos squared of x from 0 to infinity evaluated, plus we have to differentiate the cosine squared, which becomes minus sine of 2x. So that minus and the minus from the integration by parts become a plus 2 times the integral 0 to infinity sine of 2x times tanh of x minus 1 dx. Now notice that we have to evaluate these limits, right? So at infinity, let's limit as x goes to infinity. Tanh x is just e to the x minus e to the minus x divided by e to the x plus e to the minus x, which is because it's sinh over cosh. When we take the limit as x goes to infinity, the e to the minus x terms will go to 0. Meanwhile, we'll have e to the x over e to the x, which is just 1. So that's 1. It has a horizontal asymptote. That's nice. So that means when we take the limit as x goes to infinity of tanh x minus 1, the entire thing goes to 0, which is nice because the cosine is anyways oscillating. It's undefined, limit as x goes to infinity. So it's good that, this amplitude, which is tanh x minus 1, is going to 0. That forces the limit to go to 0. And at 0, we have, this tanh is 0. At x equals 0, we have a minus 2 because the cosine of 0 is 1. So minus 2, and since it's the lower bound, will be a plus 2. So we have plus 2 times integral 0 to infinity sine 2x. Now here's where the insight comes into play, because tanh x minus 1 can be expressed as e to the x minus e to the minus x divided by e to the x plus e to the minus x minus 1, the definition, using sinh over cosh and expanding their exponentials, so dx. Now here's where the simplification is going to happen. So 2 plus 2 times integral 0 to infinity sine of 2x, e to the x minus e to the minus x minus e to the x minus e to the minus x, just taking a common denominator, divided by e to the x plus e to the minus x. This simplifies inside to give us minus 2 times e to the minus x divided by e to the x plus e to the minus x, which in the end, the entire thing I can be written as 2 minus 4 times integral 0 to infinity sine of 2x divided by 1 plus e to the 2x dx. Now again, we don't like the 2x. Do a change of variables, 2x goes to x. So we have 2 minus 2 times integral 0 to infinity sine of x divided by 1 plus e to the x dx. But we want to use our geometric series. Whenever you see a 1 over 1 plus something, you want to use your geometric series. The problem is e to the x is not in its radius of convergence. We want e to the x to be less this, whatever term is added with the 1 in the denominator, we want that to be less than 1. E to the x is not a good candidate, but I know what is. E to the minus x is. So 2 minus 2 times integral 0 to infinity sine of x e to the minus x divided by 1 plus e to the minus x dx. Now e to the minus x is between 0 and 1 on 0 to infinity, and that works. It has to be less than 1, and that's it. We've satisfied the criteria. We expand the geometric series. So 2 minus 2 times integral 0 to infinity sum from n equals 1 to infinity minus 1 to the n minus 1 e to the minus x sine of x dx. So this is the formula a times r to the n minus 1. In this case, a, which is the first term, is e to the minus x, and the common ratio is e to the minus x, negative e to the minus x. That's why we get the alternating signs here. And again, now the geometric series converges well within its radius of convergence, and we could even have used dominated convergence theorem for this. But the point is, none of this really matters right now, because we have to evaluate this. I'm not going to get into the details. I could if I wanted to. It's a choice. If people want me to, I can still explain in the comment section why this we can use the dominated convergence theorem and interchange these sums and integrals exactly. But let's just go with the flow. So 2 minus 2 times sum from n equals 1 to infinity minus 1 to the n minus 1. I'm just taking the sum and integral and interchange them. Integral 0 to infinity e to the minus nx sine of x dx. Now this is just the Laplace transform of the sine function, with the output variable being, instead of s as it usually is, it's n. So it's going to be 1 over n squared plus 1 using the Laplace transform tables, or just doing the integration by parts a bunch of times, twice. So we get 2 minus 2 times sum from n equals 1 to infinity minus 1 to the n minus 1 over n squared plus 1. So it comes down to just solving this infinite sum now. And there is a nice formula for that. We know that hyperbolic cosecant of x, CSCH of x, is 1 over x plus 2 times x times sum from n equals 1 to infinity minus 1 to the n over x squared plus pi squared n squared. So hyperbolic cosecant of pi is going to be 1 over pi plus 2 pi sum from n equals 1 to infinity minus 1 to the n over pi squared times n squared plus 1. So we get pi times hyperbolic cosecant of pi equals 1 minus 2 times sum from n equals 1 to infinity minus 1 to the n minus 1 over n squared plus 1. And that means the integral, which was this entire thing, is just plugging this realization in, is 2 plus pi times hyperbolic cosecant of pi minus 1, which is 1 plus pi times hyperbolic cosecant of pi. Now, since there's a little more time, for all those people who are confused how we got this formula, it's related to the Mittag-Leffler expansion for the cotangent function. Remember, we had this Mittag-Leffler expansion. You can either derive this on its own, or you can take the infinite product representation for the sine, take the natural log on both sides, and then differentiate, because natural log of cosine, if we take the derivative, is going to be cotangent. So from that, we know the Mittag-Leffler expansion is pi times cotangent pi z equals 1 over z plus 2 times sum from n equals 1 to infinity z over z squared minus 1. Since we have hyperbolic functions, we can convert this using the appropriate conversion from the circular functions to the hyperbolic functions. We get pi times cot of z equals 1 over z plus 2 times sum from n equals 1 to infinity z over z squared plus n squared. And that the denominator should look similar. Now we claim that pi times hyperbolic cosecant of x, which is basically what we want to solve for, equals pi times cot of x over 2 minus cot of x. Let's prove this claim. So let's take the right hand side. Pi times, now expand the hyperbolic cotangents using their definition. So e to the x over 2 plus e to the minus x over 2 divided by e to the x over 2 minus e to the minus x over 2 minus e to the x plus e to the minus x divided by e to the x minus e to the minus x. So we get pi times, we can just simplify these things, 1 plus e to the x over e to the x minus 1 minus e to the x plus e to the minus x divided by e to the x minus e to the minus x. Then we get pi times e to the x minus e to the minus x plus e to the 2x minus 1 minus e to the 2x plus e to the x minus 1 plus e to the minus x. This is when we take the common denominator, the LCM, divided by the product of these two things. So e to the x minus 1 times e to the x minus e to the minus x. The numerator simplifies to give us pi times 2 times e to the x minus 2 divided by e to the x minus 1 times e to the x minus e to the minus x. So e to the x, we can take the 2 out. We get e to the x minus 1, which cancels with the denominator nicely. So we just get pi times 2 over e to the x minus e to the minus x, which is just 1 over hyperbolic sine of x, which is hyperbolic cosecant of x. So pi times hyperbolic cosecant of x. And that's it. We've proved it. Now let's prove the formula. Because if we expand both the hyperbolic cotangents using their Mittag-Leffler expansions, we get 2 over x plus sum from n equals 1 to infinity, 4x over x squared plus 2n the whole squared, because we had x over 2 the whole squared and just refactoring the 2 out, minus 1 over x minus sum from n equals 1 to infinity, 2x over x squared plus n squared. So we notice that this can be written as 1 over x, because 2 over x minus 1 over x is 1 over x plus 4 times. We can reindex this entire thing to be the sum over all even numbers. So n is even and, basically greater than 0. So 2, 4, 6, 8, and so on. X over x squared plus n squared minus 2 times sum from n equals 1 to infinity, x over x squared plus n squared. Okay. Now notice we can split the second sum as well into its even and odd parts. So we have 1 over x plus 4 times sum over all even integers that are greater than 0. X over x squared plus n squared minus 2 times the sum from n even, x over x squared plus n squared minus 2 times sum of n odd, x over x squared plus n squared. Now when n is even, the 4 minus 2 will give us 2 times, whatever summand we have. And when n is odd, then we just have this term, because, these terms contribute to the even. The even contribution has a positive sign. The odd contribution has a minus sign. This has a plus sign. The even contribution has a plus sign. The odd has a minus sign. So we can club them together. So when we have a sum from n equals 1 to infinity, since n equals 1, the 1 is odd, we have minus 1 to the n. So 1, 3, 5, 7, all the odd numbers, we get a minus sign, times x over x squared plus n squared. And then for the even numbers, we get a plus sign. We have a prefactor of 2 and we're adding 1 over x. And that's precisely the formula for pi times hyperbolic cosecant of x that we had before. And from that, it basically follows that this entire thing, integral 0 to infinity, product n equals 1 to infinity, secant of hyperbolic secant of x over 2 to the n plus 1 over secant of x over 2 to the n plus 1, quantity raised to the 2 to the nth power dx, is just 1 plus pi times hyperbolic cosecant of pi. And that's it. We're done. If I had insisted that I do the integral that I got after solving the infinite product by complex analysis, then I would have needed 2 videos. But we've done that kind of video for the old second part of this problem, which I'm going to keep because I think it's nice. People ask me why I'm doing this, or why, when I could just use geometric series like this nicely. I said, well, it's a good exercise, rectangular contours with large contributions, asymptotic contributions that don't really vanish, and making the appropriate choice. And I think that's one of the hardest questions of complex contour integration that anyone can come across, apart from maybe branch cuts with their sign ambiguities. Anyways, let's end this video here. Thanks for whoever mentioned that I should rectify, but I'm requesting, please be more specific about the literature or the timestamp reference in the comment so that I know that you're legitimate. Anyways, please like and subscribe to my channel, guys, and peace out.